Welcome class to our Skill 3 video notes outline from Unit 2B. This outline will be focusing on the method we will use for solving polynomial equations of higher degrees. And the primary method that we'll be using in this video is factoring. That is why Skill 3 follows Skill 2, which is how to factor polynomial equations, because now we are going to factor polynomial expressions so that when we have an equation, we can solve that equation through factoring. So that will be our primary method. Now, slight disclaimer here, there are other methods to solving polynomial equations, but we save those methods for when you are in pre-calculus. You will learn about other ways of solving a polynomial equation besides factoring. But in Algebra 2, we focus primarily on how you can solve. One option for solving a polynomial equation is through factoring. So that's what we will be doing in this video. And then you can see here, there's a few reminders about the types of factoring that you are familiar with at this time. First thing is to always look for a GCF. Okay, take a GCF out if there is one. Second thing is, it depends on how many terms you have. That will decide what type of factoring we do. When there are two terms, we check to see if it's possibly a difference of two squares, or maybe it's a sum of two cubes, or a difference of two cubes, and then we use the formulas for those to get the factors. If there are three terms, we use the method for trinomial factoring that we learned in Unit 2A, so that's from your Skill 4 outline. But that's basically when you make this little x and you multiply a and c together and write b at the bottom, and then you find two numbers that multiply to a and c and then add to b and then go from there. Or perhaps the trinomial is a perfect square and we have a formula for that to get the factors, which you're welcome to use too when it applies. Then if we have more than three terms, meaning four terms, we basically factor that by grouping, which we looked at on our Skill 2 outline from this unit. So these are basically the options we have at this time. So these are the things we will use to factor. Now, I should say that before we factor, really, we should have gotten one side of our equation equal to 0. Really, that's how we should begin any solving by factoring type of problem. Because once you get your factors, then you use what's called the zero product property. The zero product property is this idea that if you have one or two or three different factors that are all multiplying together to equal 0, well, one of those factors has to be 0. That's sort of the logic behind the zero product property. This was something that we had covered in the Skill 5 outline from Unit 2A, which I invite you to look back at, as it went more into detail on the zero product property then. But again, to use the zero product property means one side of your equation has to equal 0 in order for that to work. So once you've set each factor to 0, you basically have these really simple equations to solve, and then you just solve each equation. However, sometimes our factors are quadratic, especially when you're using a sum of cubes or difference of cubes formula. One of the factors in those formulas is always a quadratic. That's not factorable. So in that instance, you'll have to use the quadratic formula, or sometimes you can use completing the square to solve that remaining quadratic. So one other thing to keep in mind as well, to know how many solutions you're finding, is that the number of solutions that there are will equal the highest exponent in the polynomial. So whatever the highest exponent is, that's telling you how many solutions you will have. And remember, every time you solve a quadratic equation, you end up with two solutions. So if you're missing two solutions, chances are it has to do with that remaining quadratic. So keep that in mind. Your number of solutions should match the highest exponent in your polynomial. So let's go ahead and start with number 1. So notice the highest exponent in number 1 is 3. So what that tells me is this equation is going to have 3 solutions. So that means I'm either going to end up with 3 factors that each have a single solution, or maybe I'll end up with one linear factor and one quadratic factor, where one will have one solution and the other will have 2. So let's start by noticing that this polynomial here has a GCF of x. So I'm going to start by factoring out an x, and that leaves me with 2x squared minus 9x minus 18. And all of this right now is all equal to 0. So right now I want you to point out x is one of our factors. So the factors don't have to be binomials. One of your factors could just be a single x or a single term. Okay, but then what I have left is this quadratic here, 2x squared minus 9x minus 18. And so I'm going to attempt to factor that remaining quadratic. Okay, so I'm going to multiply the 2 and the negative 18 to get negative 36, and then write the negative 9 down here. So my job is to find two numbers that multiply to negative 36 and at the same time add up to negative 9. So there's varying combinations of things that multiply to 36. 2 and 18, of course, is one of them. 9 and 4 would be a pair. 6 and 6 would be a pair. But so far, none of those are adding up to equal negative 9, because I need to find the two numbers that multiply to negative 36 and then at the same time add to negative 9. So I'm thinking maybe I'll start with 6 and 6. So 6 and 6 didn't work, but those are two easy numbers that I know multiply to 36. So maybe I'll try splitting this 6 into 2 and 3, and then I can try mixing these factors up, right? 6 and 3 and 2. I can try different combos, like 6 times 3, that'd be 18 and 2, but we already know that, and that doesn't work. But I could try 6 and 2, which is 12, and 3. And there we go. 6 and 2, which makes 12, is one factor. 3 is my other factor. If I make 12 negative, then they'll add to negative 9. So there are my factors. So I'm going to go ahead and split that middle term into these two factors, negative 12 and 3. I keep the 2x squared the same. I keep the negative 18 the same. All of it's equal to 0. Then I will group the first two, group the last two, take the GCF out from each group. So I had a GCF of 2x in the first group, a GCF of 3 in the second group. And then now my GCF is the common binomial factor of x minus 6, right? So I'm going to take an x minus 6 out of each of these groups, and I will be left with 2x plus 3. So there you have it. This one did have three factors, three linear factors. Each one of these factors is to the first power. So that's 1 factor, 2 factor, 3 factor. The three factors are multiplying together to equal 0. This is the perfect candidate for zero product property. Now I just take each of those factors, set them equal to 0, and solve for x. So one solution is just x equals 0. That one's done. This solution would be x equals 6. That's my second one. And then this one here, I just have to subtract 3, divide by 2, and I get x equals negative 3/2 as my third solution. I knew that there would be 3 because of the highest exponent, so I was thinking there might be 3 factors, and then sure enough there were, and each one of them led to one of my answers. So let's take a look at number 2. Highest exponent in number 2 again is 3, right? So I should be looking for 3 solutions. And you might be wondering, how does a person get 3 solutions from such a simple equation? Well, because this is a sum of cubes. And a sum of cubes has this formula for factoring. So any expression of this form, a cubed plus b cubed, will factor into one linear factor, a plus b, and one quadratic factor, a squared minus ab plus b squared. Now in this particular example, a is x and b is 5, because x cubed is x cubed and 5 cubed is 125, right? So really it's kind of like this. It's in the a cubed plus b cubed format, so then its factors will follow this template here. So I fill everything in, And I can see that x cubed plus 125 factors into x plus 5 times x squared minus 5x plus 25. And meanwhile, this sum of cubes has been set equal to 0, which means this linear factor times this quadratic factor equals 0, which means both the linear factor must be or could be 0, or the quadratic factor could be 0. So you set each of them equal to 0. The linear factor I can solve by subtracting 5, and I get one of my solutions. Now let's talk about this quadratic factor. I want to point out something here to you. Any equation of this format that is a sum of cubes or a difference of cubes is a cubic function, right? It's x to the third. It's a cubic function in HK form. So I want to kind of point that out. It's in HK form where the h is 0. So this equation, y equals x cubed plus 125, is a cubic function in HK form where, in this case, a is 1, h is 0, and k is 125. So it's a cubic function that looks just like the parent graph of x cubed, and it doesn't have any left or right shift. So if it's a sum or difference of cubes, it will only have a k value, no h value, because it would just be x cubed plus some number. So this is a cubic function that has been shifted up to a y-intercept of 125. It would look something like this. Here's the y value of 125. The h for this is 0, and the k is 125. So that forms the middle of your graph. This is the middle of your graph. And the a value is 1. So there's no stretch or reflection or anything. So the graph will look something like this. This is a very not to scale sketch, but it's that squiggly shape that we had looked at before break. And I'll show you, it only hits the x-axis. It will only ever hit the x-axis one time. In fact, I can tell you for this particular graph, because one of my solutions to this equation is -5, that's going to be where it hits the x-axis. That'll be my single x-intercept there. So then what does that tell me about this remaining quadratic factor? If this graph is basically just an x cubed graph, right? X cubed graphs basically just look like this, little squiggles. If it's just basically that graph shifted up to 125, then I know it's only ever going to have one x-intercept. So what that means about the solutions to this is that they always will end up being imaginary numbers. So that's another reason why when we factor these, we stop here, because we know that this quadratic will never factor. Now, in the instructions earlier, it asked us to find all solutions, both the real ones like -5 and the complex ones, which include numbers with I in them. That'll come from this quadratic part of the sum or difference of cubes formula. So I'm going to find those by using the quadratic formula. So the solutions to this equation here will be -b plus or minus the square root of b squared minus 4ac all over 2a, which in this case is just 1. So I just need to simplify this expression here. So I get 5 plus or minus the square root of, oh, I notice I made a mistake here. This should just be 25, not 25 squared. It was 5 squared, right? B squared, or -5 squared is 25. So I get 25 minus 100, because 4 times 25 is 100, all over 2. So then that gives me 5 plus or minus the square root of -75 all over 2. And I can simplify the square root of 75 a little bit because it's got a factor of 25, right? 25 times 3. And 25 is a perfect square. So because of that, I can simplify this square root a little bit. But also, I need to be aware that whenever I have a -1 under the radical sign, I understand that is an imaginary number. So when I pull out the perfect square of 5, I also put an I in front of that square root. Then the single factor of 3, right? 5 times 5 times 3 makes 75. That single factor of 3 remains under the radical. The perfect square, the double 5s are pulled out. Take the square root of that as 5. The negative 1, right? The square root of negative 1, we call it I. And all of that is over 2. So these would be the other two solutions. Because you've got a plus or minus sign, 5 plus 5i rad 3 over 2 and 5 minus 5i rad 3 over 2, this actually counts as two imaginary solutions. So for number 2, the three solutions we ended up having were negative 5 for the first one, 5 plus 5i rad 3 over 2 for the second one, and 5 minus 5i rad 3 over 2 for the third one. Now, because these two solutions have I in them, that is why this graph will only ever have one x-intercept. Solutions that are imaginary do not appear on the graph as x-intercepts. Only real solutions do. So that is why this graph would only hit the x-axis once at negative 5. But it still has a total of 3 solutions to this equation. The same is true over here for number 3. But number 3 could be very deceiving, very misleading, especially if you're being asked to find all solutions, which we are here. It would be very easy to start by dividing both sides by 8 and say, okay, x cubed is 1 over 8, and then cube rooting, right? Cube rooting both sides, and then we get x is equal to 1/2, right? Because 1/2 would be the cube root of 1 over 8, since 1/2 times 1/2 times 1/2 is 1/8. And then you'd say, okay, I'm done. That's all my solutions. It is one of the solutions. One of the solutions will be 1/2, but there are 2 more, and the only way we can find them is by using this formula to factor this difference of cubes. So we're going to scratch that. Okay, so don't fall into that trap. We want to start by getting one side of this equation equal to 0. So I'm going to start by subtracting 1, like that. And I can see that, okay, this is actually in the form of a difference of cubes. It looks very much like that form, where a would be 2 and x together, and b would be 1. Okay? And so I'm going to follow the formula for a difference of cubes to get my 1 linear factor and my 1 quadratic factor. So I plug in 2x for all the a's and then 1 for b. And so these would be my 2 factors. 2x minus 1, 2x squared, which is 4x squared, plus 2x times 1, which is 2x, and then plus, right, third sign is always positive, 1 squared, which is 1. So I have 1 linear factor, 1 quadratic factor, all of it's being set equal to 0. So I can use the zero product property to say, okay, that means either 2x minus 1 is 0, or 4x squared plus 2x plus 1 is causing the 0. This linear factor over here, when I solve it, gets me that 1/2 that I found originally. Right? So I get x equals 1/2. So that really was one of the solutions. One of the solutions will be 1/2. But this quadratic here will get me the other 2, just like we saw in example 2. When I solve it using the quadratic formula, it will leave me with these 2 solutions with the I in them. Because as we've seen, this quadratic part of a sum or difference of cubes always ends up giving imaginary solutions. So we'll see that again here as well. So again, I'm going to solve this part by using the quadratic formula. So negative b plus or minus the square root of b squared minus 4ac all over 2a. So in this case, that equals negative 2 plus or minus the square root of 4 minus 16 all over 8. And then I can simplify that further. So I have negative 2 plus or minus the square root of negative 12 all over 8. Now, that square root of negative 12 can be simplified, just like the square root of negative 75 was earlier. First thing I notice is the negative, right? I'm going to have to take I out of this radical like I did earlier here when it was the square root of negative 75. And then also I noticed that 12 can be broken into 4, which is a perfect square, and 3, a non-perfect square. So I can square root the 4 and get 2. So I'm going to pull out a 2 and I, and then leave in a 3. So I get negative 2 from here, plus or minus 2 from the square root of 4, I from the square root of negative 1, and 3 from the single factor of 3 left over from the number 12. Okay, but this one I need to do some further simplifying, right? Because it's got common factor of 2 in the numerator, so I'm going to pull that common factor out. So then this would leave me with negative 1. 2i would leave me with just 1i rad 3, and that's all over 8. And then I can cross out the 2 with the 8. I can divide 2 into 8, which leaves a 4 in the denominator. And my other two solutions for example 3 would be negative 1 plus or minus I root 3. These here are my two imaginary solutions for number 3. This is part of my answer to number 3. One of my answers was x equals 1/2. That was my one real answer. And these are my two imaginary answers. Negative 1 plus or minus I times the square root of 3. Remember, the plus or minus makes it two solutions. So that's how I can say that I have 3 solutions total. Okay, so coming over to number 4, I sort of took all the space here for numbers 2 and 3 and didn't leave myself a lot of room here for number 4. So I'm going to move this out of the way a little bit and carve out some space to work out number 4. Okay, so one thing I do notice with number 4 right off the bat is it does have a GCF of x. So I like that actually, because I know that that's one of my factors, right? GCF of x. When I factor that GCF out, I'm left with 4x squared minus 9. Now the thing that I notice about 4x squared minus 9 is that there's only 2 terms, and both of them are perfect squares, and there's a subtraction between them. That makes this a difference of squares. So I will factor this according to the difference of squares property, which is on your Skill 4 notes from Unit 2A or from your Skill 2 notes from this unit. And then lo and behold, there are my 3 factors. And I knew that this would have 3 solutions because the highest exponent is 3, and each one of them will come from one of these 3 factors. So one of them is x equals 0. That's one answer. The other answer will come from when I set 2x plus 3 equal to 0. I just need to solve that. So my other answer is negative 3/2. And then my third answer will come from when I set 2x minus 3 equal to 0. Add 3 to both sides. Divide by 2. And my third answer is positive 3 over 2. So first answer was 0, which came from the x factor. Second answer was negative 3/2, which came from the 2x plus 3 factor. Third answer was positive 3/2, which came from the 2x minus 3 factor. Okay, moving on to number 5. Again, I want to point out, you want to make sure you get 0 on one side before you start factoring. So I'm going to go ahead and subtract the 9x over to the left side here. And I'm going to be sure to fit it in the spot where it would belong. And I'm going to make sure to fit it in between the x squared and the 18 term. And that would put it in the right spot if I was in descending order. Right? And let me carve out some space for this one too, so I don't get confused here. Okay, so then what I notice when I bring the negative 9x over is now I have 4 terms on the left. It's a 4-term polynomial, and we graph those by grouping. We group the first 2 terms, we group the second 2 terms, we take out the GCF of the first 2, which in this case is x squared. The GCF between those 2, which in this case is negative 9. Then we go, okay, now I have a common binomial, x plus 2. I can factor that out. And when I factor that out from this chunk and that chunk, I'm left with an x squared and a minus 9. Haha, sneaky little buggers. These differences of squares like to sneak in, right? X squared minus 9 can keep factoring because when you think about it, it's a quadratic, right? X squared. It's two terms. Both of them are perfect squares, and there's a subtraction between them. It's a difference of squares. So that's x plus 3 and x minus 3 according to the difference of squares formula. So like with the last problem, number 4, I'm left with 3 linear factors. Each one will give me one solution. All I have left to do is set each one equal to 0 and solve for x. This solution is going to end up being negative 2. This solution is going to end up being negative 3. And this solution will end up being positive 3. You may start to notice as you do multiple of these that when you have linear factors like these here, the solution is always just the opposite sign, right? So it's okay if you can recognize that. You can say, okay, I know this one will be negative 2, that'll be negative 3, that'll be positive 3, and just list those 3 solutions. That's okay. All right, last but not least, number 6. Again, be careful and make sure that you get 0 on one side. So you want to start by adding 1 to the left side, okay? And since that's the constant, that one should go at the end. And now the whole thing's equal to 0, making it easy to set equal to 0 once we get the factors. To get the factors, since there's 4 terms, we're going to go ahead and group the first 2 and group the last 2. Now when we group the first 2, I notice they have a 2 and an x cubed in common. So I'm going to pull out the 2x cubed, okay? And then when I do that, I'm left with 3x plus 1, right? 2x cubed divided by 2x cubed is 1. Meanwhile, over here, there's really nothing in common, so we kind of think of that as just having a common factor of 1. So I'll kind of write it that way so that I can go ahead and factor out my common factor of 3x plus 1. So I will take my 3x plus 1 out, and that leaves me with 2x cubed plus 1 is equal to 0. So I can see here that if I set each of these factors equal to 0, well, I'll get one solution from this linear factor. I get x equals negative 1/3. And then I'll get a second real solution from this cubic factor. So this is a cubic factor here. Now the thing with this one, I know this has 3 solutions, right? Because the highest power is 3. But because this is not a perfect cube, the 2 is not a perfect cube, I could factor this using the sum of cubes formula. I could just think of a as the cube root of 2. But at this level in Algebra 2, I'm not going to make you do that. So we'll go ahead and find the second real solution. The second real solution would be this. I would subtract 1 from both sides and divide by 2. And I'll get x to the 3rd is equal to negative 1/2. Then we would take the cube root of that, the cube root of negative 1/2. And that is basically, well, you can't really simplify it that much other than to just pull the negative out in front, because there is no perfect cube root of 2. So I'll just pull the negative out in front, and I'll think of that as just the cube root of 1/2. With a calculator, I can get a decimal value for this number. It's a real number. You can have negatives underneath cube roots, right? Just not underneath square roots. Now I know that there are 2 other imaginary solutions. If I were to factor this out using the sum of cubes formula and using a as the cube root of 2, I could solve for those other 2 imaginary solutions. But at this level, we're going to just stop here for this particular one, since 2 is not a perfect cube, and just find these 2 real answers. Now, how do I know there's 2 imaginary solutions? Because of this highest exponent of 4. That tells me that I should have 4 solutions total when I solve for this. So I'm just going to write a little note here that there are 2 additional imaginary solutions. And we'll kind of stop there with that for this one here. So there's 2 real solutions, negative 1/3, negative cube root of 1/2. And then there are 2 additional imaginary solutions that would come from the quadratic factor of this that we will not bother to find here since 2 is not a perfect cube. So we'll end this section here, and I will see you tomorrow in class.